Hello everyone. In this notebook, teaches about retrieval augmented generation or RAG by building it end to end. We load PDFs, chunk text, embed chunks, retrieve relevant context, and generate a grounded answers with OpenAI. The goal is not just to make it work, but to understand the design trade-offs and debugging workflow. Now I'll go about installing the dependencies required. If you're running in a fresh environment, install dependencies here. In this repo, these go into requirements.txt. For this demo, I've already installed them. So next, I'll go to the setup section. So here in this section, this sets up libraries, keys, and verifies. We can call the OpenAI API. I'm keeping the notebook beginner friendly and reproducible. Next, I'll go talking about the imports. These imports cover PDF parsing tools such as PyPDF, embeddings using sentence transformers, vector math using NumPy, ENV loading, and OpenAI client. The next cell I'll be talking about the API key and OpenAI client setup. So we load the OpenAI API key from the environment variable or the .env file. You set a model name. I'm using GPT 4.1 mini for cost and quality balance. This ensures the pipeline can generate answers later. Next I'll talk about the LLM wrapper rational. I wrap the OpenAI client so that the rest of the notebook stays clean. This makes it easy to swap models later without rewriting the pipeline. Next I'll talk about the OpenAI LLM client wrapper. This generate method takes a prompt and returns the assistant output, keeping the LLM call isolated, which is good architecture and improves maintainability. So next I'll talk about what is RAG. RAG is retrieval plus generation. We retrieve relevant document chunks and give them to LLMs as context. This matters because LLMs hallucinate and don't know your private PDFs. Retrieval grounds the answer in your data. So in this notebooks, PDFs are our knowledge base. So first I'll talk about how to loading a PDF. So step one is ingestion. So we load PDFs and extract their text. If extraction is basically garbage, everything downstream fails. That is a classic example of GIGO, which is garbage in, garbage out. So next I'll show about how we have loaded PDFs. Okay, just a second. This just needs to be run from before, so else we face an issue over here. So this let these imports run. I forgot to run this earlier. So once this runs and all of the imports get completed, this the next these part will load, and basically I'll just show you how this notebook works end to end. So it's better if I show you rather than me just telling how the things work. So basically you can see I have put three papers, which is paper 1.pdf, paper 2.pdf, and paper 3.pdf. So basically I'm just putting data here and basically chunking characters out of this one. So basically in this thing, the code which is put here, this function reads one or more PDFs and concatenates extracted text. I point to the folder where I store the PDFs. If a PDF is scanned like image only, extract text may return empty. That's a common failure in this kind of extractions. So in the next thing, I preview the extracted text. I print character count and I preview the first 1000 characters. This is my first sanity check. If the text is empty or weird, the RAG won't work. So basically you can see what I was talking about. So if basically you're getting anything empty over here, you will see that the RAG is not working. Next I'll tell you about the chunking concept. We chunk because embeddings plus retrieval works best on smaller passages. So the chunk size and overlap are trade-offs. Bigger chunks give more context, smaller chunks give more precision. So basically, this the context of what we were trying to tell. So I'll go on explaining with the code. So let me run this side by side. So here, what we can understand is this is a word-based chunker with overlap. Overlap prevents chopping ideas mid-sentence. We create a list of chunks that will become retrievable units. Next, I'll run this part also. So here you can see yeah, this lets us visually confirm chunks look coherent. If chunks are messy, retrieval relevance drops. So that is something we need to look after. So in this next cell, I'll be explaining about how embeddings convert text to vectors in a semantic space, which means the similar meaning, which essentially says that vectors are close to each other. We'll embed both document chunks and the user query. So let me start running this. So basically, let this complete. Oh, this has completely run now. So here, what we load all of them into all mini LMV L6 V2, which is a lightweight, good enough model for teaching. We'll embed all chunks once, producing a matrix called num chunks and embedding dimensions. This embedding matrix is what the retriever searches for, and basically you get the output over here. So next, I will tell about a simple vector store. Instead of using a full vector database, we build an in-memory vector store to keep everything transparent. This makes the cosine similarity and retrieval logic visible for learning. So um, So cosine similarity plus a simple vector store. I'll show it as a code now. Cosine similarity measures angle between vectors, perfect for semantic search. The store keeps chunk embeddings plus original chunk text. Search returns the top k most similar chunks. And the next we see about the test retrieval without LLM. Before calling the LLM, we validate the retrieval alone. If retrieval is wrong, the LLM will confidently answer nonsense. So basically, if you give the LLM some very basic chunks, and if it is not being retrieved properly, the LLM will answer on behalf of us and will be confident about its approach also. So we retrieve and print the top chunks over here. So basically, you can see all of the top chunks which are here. So we embed the question and retrieve the top k chunks. I print the chunks and similarity scores. This is interpretability. We see what evidence the model will use. Next, I'll talk about retrieval plus generation. Now we connect retrieval to generation. We build a prompt that includes retrieved context and instruct the LLMs to use only that context. Um, so the prompt has three parts: context, question, and strict instructions. The rule is if answer isn't in context, say I don't know. This reduces hallucination and trains grounded behavior. So basically, I'm doing with answer with drag and run a question. This is the full drag orchestration: retrieve, prompt, and generate. We run a question and capture both the final answer and the retrieved chunks. So and then finally print the retrieved chunks for transparency. I print retrieved chunks again so we can verify grounding. This is essential for computational skepticism. Don't trust the answer and just go on verifying it. So next is a try segment, which is basically the exercises I have built. So let's go on doing this also. So exercise 1 tests how chunk sizes and overlap affect retrieval and answer quality. The learning point here is chunking is not cosmetic. It changes the behavior of the whole system. So let me run and show this to you. Let this part run so that the next part runs properly. So basically you can see the how the visualization is coming here. So we build a pipeline for multiple chunk settings and compare. This runs the same question under multiple chunking strategies. We compare retrieval relevance and answer quality across settings. So we visualize the retrieval similarity distribution, which is the exercise 1. These plots show how well the retriever separates relevant versus irrelevant chunks. A strong retriever gives a steep drop off, like here. Top chunks score much higher than the rest. So these are the top chunks coming in, and a flat curve means poor retrieved signal. So since I don't see a flat curve here, so this essentially means Um okay, so here you see a flat curve. So this means a poor retrieval signal. So next I'll talk about exercise 2, how we can how what is exercise 2. So basically exercise 2 expands the corpus to multiple PDFs. So the goal here is to prove retrieval work across documents, and that the right PDF wins for the right question. So let me run this, and I'll let you guys know how this is working. So here I load multiple PDFs into the pipeline, rebuild embeddings, and run two different questions. The expected behavior. Each question retrieves chunks from its relevant document. So yeah, I rebuild chunks with document labels fixed for multi-doc labeling. The cell chunks each PDF separately and assigns labels at a chunk creation. This avoids slow or buggy guessing or of chunk provenance after concatenation. Now I can track which document each retrieved chunk came from. So basically, this is what I was talking about. So you can see here how the chunks are. Once I visualize them, the chunk shows similarity across all chunks and prints which PDF each retrieved chunk. This is basically how we verify multi-document correctness. So next I'll go about talking about exercise 3. So here in exercise 3, uh, we introduced similarity threshold. This is a precision tool. Filter weaker matches so that the model don't see any noisy context, but too high a threshold can retrieve nothing. A meaningful failure mode. So in this cell, I'll show you how this runs. So let this complete running. Okay. So here I modify it to accept threshold argument. Basically, then I compare retrieval with and without threshold and observe answer changes. This teaches retrieval quality control. So threshold affects visualization. The plot shows similarity scores with the threshold line. Chunks above the line are eligible. Below are filtered. This makes threshold tuning visually intuitive. So in the next, I can do a similar scatter plot, which I've not done, as this is an optional case. This will show a ranked similarity shape. A steep drop, which is equal to a strong signal, which are flat curve shows a weak signal. It is a quick diagnostic for embedding plus chunk quality. Next, I'll go about the debugging notes. This section documents common failure points: bad PDF extraction, bad chunks, irrelevant retrieval hallucinations, speed issues. This is practical troubleshooting, not theory. So let me show them in practical ones. Automated debugging suite. This cell runs a full diagnostic, checks text extraction, chunk count, embedding shape, retrieval, success, prompt preview, and LLM output. It provides actionable errors, great for learners and graders. So basically, you can see the entire thing which we did. I'm like putting this as a validation so that whatever we did can be validated, and see that whatever we've done up until now makes sense at the end. Finally, going on to wrap this up, so we built a full rack pipeline from scratch and proved it works on a single and multiple PDFs. We tested chunking, thresholding, and retrieval interpretability with visualization. Next steps for production. I can connect this to a vector database like FAISS or Pinecone DB for man metadata filters, re-rankers, evaluation metrics, and a UI like Streamlit. So basically, this is what I was talking about. So doing all of this will create an end-to-end back-end and front-end of the application, thus completing what we wanted to learn about track and how the components connect to each other to create an end-to-end pipeline. So thank you everyone.